Sounds great to me. So welcome everyone. My name is Holger, and I would love to give you an introduction into how to do process modeling. And I would like to pick on where we left in the morning. So I would like to talk about how to use Kotlin to enable process modeling using a library which I'm maintaining, which is called kalasim. And the idea and the main intent of this presentation is really to understand how we can model and optimize real-world processes. And yeah, I would like to take you on a journey or where we want to go to the moon. We will talk about how to make a lot of money. We will talk about processes, business processes, various types of them. And for sure, we will also talk about technology. So we want to understand and to study how we can use Kotlin to model different processes. So you may wonder, why do I care about it? Like, do I care about process modeling? And I'm not so sure if everyone is familiar with the great TV series called Westworld. If you haven't seen it, I think you should consider stopping this lecture right away and going to your TV and start watching it, because it's actually a great series. It's not a Western series, as it may seem from the screencast here, but it's actually a science fiction series, which is about robots which have a very complicated process model. It's actually so complex that they can mimic actual human beings. And the series is about how humans and those very realistic robots interact with each other, how the robots develop some consciousness. And it's a really great series, so give it a try later. And one of the favorite quotes of the series is when this lady, and she's called Dolores, says that some people choose to see the ugliness in this world, the disarray. I choose to see the beauty, to believe there is an order to our days. And I think it's really a great quote. And because it says that even if everything may seem chaotic and unstructured, there is actually structure. And I think this also applies to processes around us, manufacturing processes, business processes, real world and real life processes. But the problem is that usually there's so many processes going on in parallel that may seem unstructured. But today we will want to learn about how to decompose complex business processes into more atomic processes so that we can manage and model them more easily. What's the schedule for today? I would like to start with a brief introduction. I will then describe how I and my colleagues analyze processes, in particular in manufacturing. Then I would like to dive into discrete event simulation. We'll then talk about this library I was mentioning. So we will do a quick tour through kalasim. We will then talk about how to analyze simulations, and to keep it also exciting for you, we will then try to do an exercise. I think this might be a bit tricky given a huge number of participants, but I think we should try nevertheless, because I think you should get some first-hand experience how you can use Kotlin to model processes. I would like then take you on a journey, as I promised, to the moon. So we will talk about process animation. And we will then briefly discuss how we can use process models and simulation in general to achieve optimization. So how to optimize processes to perform better. If there's time left, we have to see, we could do another exercise block. And at the very end, for sure, we will sum up what we've learned, and we can discuss next steps for you. And I will also give a brief overview about what I and my colleagues plan to do regarding simulation. So before diving into the technical details, allow me to briefly introduce myself. So I started my career at Honda in collaboration with the University of Bielefeld in Germany, where I was doing humanoid robot research. So my project was about building a model that enables the humanoid robot to learn the structure of human language, similar to how infants do. Later on, I moved to systems biology. So I joined the Max Planck Society in Germany and studied for, I think, almost 10 years, the very exciting questions how cells form tissues. And yeah, later in 2019, I then moved on and joined a company called SYSTEMA. So I joined industry, where we deal with process automation, in particular in manufacturing. So in parallel to what I was doing or what I am doing professionally, I was always curious about technology. So somehow as side projects, I developed various open source projects, and some of them are done in Kotlin. So I was writing some script utility called kscript. I wrote a couple of libraries to enable data science using Kotlin. And more recently, I started this library to model processes, which we will talk about later today. In my role as analytics solution architect at SYSTEMA, I mainly support customers to optimize their manufacturing processes. So this is a complex endeavor because usually our partners are from semiconductor industry or other complex in discrete industries. So it takes usually a lot of time and effort to first understand their processes, to model them, to finally then optimize them. And today in this presentation, I would like to give you an overview about how we approach these problems. I mean, what tools we use and what's the general order of things. So sticking to this example from a semiconductor, I think it's a very good example because it illustrates very nicely the complexities we have to deal with when optimizing a business process such as semiconductor production. First, it takes very long to produce a microchip. So sometimes it takes up to 6 months from the raw wafer to the final product. And there's usually more than 1,000 steps involved where we iteratively add layers on top of layers on the wafer. So some say that microprocessors are actually the most complex manufactured product on Earth. And this is, I think, yeah, somehow understandable because what they have to do here is they have to build some kind of skyscraper with many, many different layers stacked on top of each other, but they have to build the thing with nanometer precision. So it's a pretty exciting process. And as you can imagine, it's also a very costly process. I'm not sure to what extent you're following the semiconductor news, but building a new semiconductor fab is usually costs billions of dollars. So they are very, very curious about how to squeeze out every possible piece of productivity from these super expensive fabs. And this question is, I think, is a very general question in business. So if you have a business process, it could be a manufacturing process, it could be a call center, it could be basically any business process where different partners interact with each other. The question is very often, how can we plan, how we can guide, steer this process more efficiently to in the end make a bit more money? And this is a very complex question, and we will try to find some answers today, but for sure we cannot fully answer this question. So it's a complex interplay what we have to do. So we have the business process, which could be a manufacturing site. And the first thing what we always have to start with is we have to analyze the current process. We really have to understand who's involved, what material is involved, what are the steps which need to be realized, how do the different actors interact with each other. And once we have an idea about the process, we really need to write it down, we need to formalize, we will dig into the details later. And just once we have established this mental picture, we can start optimizing a process in order to, for instance, make more money. To work out this idea of analysis and optimization a bit better, let's look at this slide, which is essentially the same idea, but it details out the core ingredients we need to realize to optimize a business process. So for sure, there's a business process, which could be a manufacturing process, like we have a production area in a factory, and they want to optimize throughput in this area. So the first thing we need to do is we really need to work out a detailed description about what's going on there. As I said, we need to work out what's being produced, what are the steps, how long do they take, I mean, who's involved, to what extent, how much time does it take to do this and this and this. And so we really need to build a complete picture of what's happening. Once we have this complete picture, we then can start trying to build a model of the process. So this is where the simulation part. And once we have the simulation, we can start comparing the outcome of our simulation with what's happening in the real life, because typically there's always a mismatch. So I've never encountered a project where the simulation was working right from the start. So what we have to do is we have to compare the simulation outcome with the business process, and we need to understand why they differ. And then we can basically iteratively improve our process description and also our simulation. Once the simulation is up and ready and reflects the dynamics we see in the real process, we can then think about how to optimize this process. So we can think about planning, we can think about process restructuring to improve some key metrics which are most important to our business partner. And once we have assessed the feasibility of optimization techniques, we can then try to bring them back and to incorporate them into the real business process, which is another very complex endeavor depending on the industry. For instance, in semiconductor, I mean, just to work out this idea a bit better, usually there's different levels of planning. So there's, I mean, long-term scheduling where they basically plan their orders and products and ramp ups. Then they have something which is closer to operations, which they call then a production operations scheduling. And then on a very short time range, they actually do the tool dispatching where they assign specific work items to specific tools. And to understand the dynamics of such a process and to make them better, we really have to account for several of these aspects while abstracting away others, which I think is always a critical task when building working out a simulation project, because we cannot model everything. We have to abstract certain aspects or processes away which are not really relevant for our key metrics. So how do we start this? So far it was all, I guess, a bit fuzzy and abstract. So how can we actually get started? So I think what's very common is to do this so-called business process modeling. We try to take some big a board, and then we write down lots of squares and lots of arrows, and we try to really connect the different actors and entities and relations in order to write down what the business process looks like. But this is very often not sufficient to truly understand where the bottleneck in our process is. And the reason is that by just drawing the diagram, we don't really, I mean, run the process in a computer. It's not yet a computer program, it's just a drawing. So it may remain hidden where the bottleneck is. So the bottleneck we may want to address in our optimization project. So what specifically do I understand as a bottleneck? So usually a bottleneck is referred to as a process where one process reduces the capacity of the whole chain of processes. So in a factory, for instance, you could have a single tool, which, I mean, basically limits the throughput. Or in a call center, it could be some, I mean, some process which limits the throughput as well, because some agent might be a bit slower, but every process or every incoming call needs to be routed through them. And a bottleneck is a very serious problem because it really delays the process and severely impacts its performance. But why is it so hard to understand where these bottlenecks are and how to resolve them? The reason, I think, is that there's a complex interplay of the different elements and entities involved in any complex business process, because it's usually not just the staff alone, but it's a very complex interplay where we also have to account for equipment, for processes, for material, for environment, for management, and all these factors somehow contribute to the outcome of the process. And unfortunately, they very often don't do so in a linear, intuitive way, but there's some kind of non-trivial interplay of these resources, which we need to unravel. And one way to do so is to build a model. And clearly, building a model is not a new idea. So it was already discussed and formalized almost half a century ago. And I think Shannon described it very nicely when he said that a simulation is the process of designing a model of a real system and conducting experiments with this model for the purpose of either understanding the behavior of the system or of evaluating various strategies within the limits imposed by a criterion or set of criteria for the operation of the system. And I think this really describes it well. So A simulation is all about designing a model of something real. It's not the same thing. It's an abstraction. But with this abstraction, what we can do is we can perform experiments and we can try to understand the behavior of the system. And this is essentially what we want to do here. So we have our business process, which we want to improve. So first we need to build this model. And once we have it in place, we can start studying it. And once we are sure, and once we have developed an idea about its dynamics and what knobs to tune, we can then think about strategies to perform to improve the performance of our system. So let's dive into the first part of any process optimization project. So the first part is about understanding the process. So we really need to develop a formal description, a so-called process description about what's going on. How do we do so? So it's really a deep dive, because real-world processes are very complex, and at first glance, they may also feel a bit unstructured. So what we need to do is we really need to write down, I mean, what are the processes? Because there's usually not just one process alone, but usually it's a set of processes which is somehow intervened with each other. Secondly, we have to think about who are the actors. In a factory, this could be the workers, the operators, it could be engineers, could be colleagues from the logistics department, which are all interacting with resources and with each other. And in particular, these interactions, I think they deserve a lot of care to really understand who's interacting with whom. So what's the chain of responsibility here? And clearly, in any business process, decisions are always informed. And these decisions are usually informed by relying on certain data sources. And I think that's also a very important aspect, that we dive into those data sources to understand, I mean, what's available and also where are information gaps. Because, for instance, if you want to, I mean, roll out some more automatic decision-making system, we need to make sure that all the necessary data sources are digitized. And finally, what we need to think about when writing or working out the process specification is we need to formalize the control regime. So who's assigning material to a tool, who's assigning cost to a call center agent. So that's the first part. So we really need to talk to the colleagues on site, to our business partners, to understand their specific process and all its elements. And the second aspect we need to think about is the data analysis, because every process emits data in some way or another. And we really need to validate our understanding of the process written down in the process specification by studying the data which is available. And usually it's not just a single sheet or a single database, but from my experience, it's usually scattered across a wide range of different data sources. Some of them are more structured, some of them are less structured. And if you're really unlucky, it's still something on paper. And clearly, this is a process that takes time. So it's an iterative process. You start talking to some of the involved actors, and then you start talking to others. Sometimes there's even a mismatch, so they may perceive their own processes differently. So it's an iterative process where we more and more, I mean, create a dense picture of what's happening. So first step is to do the deep dive into the process of interest. The second step, the data analysis part, is somehow similar. It's not the same, but I think it's somehow similar to what data scientists do when studying data. So there's this, I mean, this very classical picture here where we say in data science, we always have to import data first. We need to clean it up. We transform it. We try to do some EDA, some visualization. We model the data. And at the very end, we can communicate our findings. And I think in process analytics and process optimization, the process is similar, because for sure the import step is not that we have a sheet or some database which we can ingest, but it's about working out or importing the process description and taking the available data snapshots as a starting point. And clearly they never come in a structured way. They always come in some kind of, more or less a messy format. So we need to, clean them. We need to tidy these data. And once we have these, we can then really start working out visualizations or visuals of the process of interest, because these are very important, because with those we can actually approach also the actors in the process to understand their perspective. With all this information and this insights in the process, we can then start working out a model. And that's in our case a simulation model. So it's not a classical machine learning type of prediction we want to do, but we use a more mechanistic model of what's happening to, in the end, prepare something which is functionally similar, because also a simulation model allows to do predictions. And once we are happy with the accuracy of our model, we can then really communicate this to our partner. And if everyone feels that the accuracy of the model is sufficient to go for the next step, which is the process optimization, then we can proceed. And clearly, this is a time-consuming process, because there's lots of data, lots of information which needs to be considered. So how do we typically approach this? So how do we do this process analysis step? And the process analysis is, as I just explained, to a huge extent data analysis. So we get data, at least that's how it works for me. So we get from our partners a lot of data, which we have to, dig through, and we need to try to map or align those data with the written and the discussed description of the process of interest. So technically, what we do here, we use R, Python, or whatever you prefer, to work out means, distributions, to assess variations over time. We perform association and correlation analysis. So we really do classical exploratory data analysis to understand the dynamics and the mechanics of the process of interest. And the outcome of this phase is usually that we want to work out all the relevant process parameters. So we need to know how many workers are there, how long does it take to do certain production steps, or how long does it take to serve a customer. As I said, basically, you're free, or we are free to choose whatever tool we like to perform this. So we could use R, use Python, or very often it's also mixed. We also usually, because the partners very often like it, we also rely on Excel to study the data, or we use some BI tool like Power BI. But I think one question which some of you may ask is, since we have heard about Kotlin as a very modern language this morning, could we also use Kotlin? And if you go to the landing page, kotlinlang.org, at first it doesn't seem so, because all they seem to talk about is multi-platform mobile, server-side, web front end, Android. But if you look carefully here, what we actually see is that also the makers of Kotlin had data science or have data science in mind when designing the language. So it's actually listed as one of the use cases, even if it's, I guess, at the moment not so present in most developers' minds. But if you dig it a bit deeper, and if you follow up on those links, there is actually a small ecosystem which colleagues are using to use Kotlin for data science. So I pulled together some links which I think are nice presentations and give nice overviews. And before proceeding, I actually want to share something else with you, which I missed initially, because you can find all the slides also online. So in case you want to put down some notes, let me share the link with you. So this is now a bit, wait 1 second. So I published all the slides on GitHub so that you could have a look. So there is docs, presentations, and there should be, yes, here it is. So these are the slides we are looking at. Yeah, I wanted to mention those earlier, but I think it's not too late yet. So what I want to do is I want to share this link with you via the Zoom chat. So let me see whether I can find the Zoom chat. Zoom. Okay, chat, here it is, very good. So I would send this link to everyone. Maybe Anton, could you confirm whether you could see the link just to make sure that I did the right thing? Oh yeah, Alex already confirmed it. Wonderful. So in case you want to have a copy of the slides, yeah, feel welcome to download them from here. So let's jump back. So this thing is solved. I shared the link to the slides with you. So let's come back here, because now you could actually also click on the links if you're curious later on. So yeah, coming back to the question. So Kotlin is actually a possible tool for data science, but it's for sure not as major as platforms like R or Python. So I think it's on a good track. It's an amazing language for modeling and prototyping. And I think there are some great projects like DataFrame, Kotlin DL, Multic, and we will also see this later on. There's also a great kernel for Jupyter. Unfortunately, I think it's still a young ecosystem. So for colleagues who are not so familiar with the Java ecosystem in general, the tooling barrier sometimes might be a bit steep. And I think this is one of the reasons why it has seen kind of slow adoption in the data science community so far. But maybe this is also just perception bias from my end. I don't know. But the beauty of using Kotlin also for data science is that, I mean, it's multi-platform ready, and you can also, if you do it on the JVM, you have this huge ecosystem of libraries which you can then use in your project. However, in productive use cases, like when I do commercial projects with customers, I typically still prefer R. I mean, I know this is an opinionated view. I guess some of you have other preferences, but I nevertheless wanted to share it with you, because I think this is also a good opportunity for us. And I'm also looking for your comments and the discussion later on to talk about what tooling we use and why. And for me, the reason to stick to R here is that it's still, in my opinion, superior when it comes to manipulating tables, mainly because of the dplyr library, which is just a great thing. And also when it comes to data visualization, I think it's still the best thing which we can get via ggplot. And finally, I think it's also superior when it comes to statistics. So, and for sure, I interface and interact a lot of colleagues who use other things. Like for sure, a lot of my colleagues are using Python, and some use Julia and other things. But to me, nobody could convince me yet to move to some other language because of these three aspects, which I think are the most important ingredients when digging into complex data sets. And yeah, I also like this quote here from John Ertz, who really summed up this idea here that statistics is about proving what you expect, while visualization is about discovering what you didn't expect. And I think this is really key when studying process data, when you get snapshots from processes, to really first to visualize them, and then to do statistics to basically really have both sides of the picture. So let me give you an example. So, I mean, for sure, we cannot analyze actual real world processes today, because this would take too long. But nevertheless, I would like to give you some glimpse about how we typically approach data. And what we see here is a production schedule. So on the X, we have time. On the Y, we have tools. And what we see is indicated by these colored bars when tools are in use. And I think this picture, I think it came from one of our projects. I think it's very interesting because it tells so many things already about the process here. So first thing it tells us that some tools, all these tools that start with ASM, they are basically fully booked. So they run basically 24/7, which could be a good thing, could be that they have excellent line control, or could be that there's a bottleneck. So this is really basically limiting their throughput. Another aspect which is very clear is that some other tools like AutoCL is essentially not used. So the question is, why do they keep it? Because keeping tools always costs money. So they may have a reason which is not obvious here. So we may need to dig deeper and talk to more colleagues on site to understand what the reasoning is to keep it around. To give you another example about process data analytics, I would like to talk about equipment utilization. It's essentially a similar picture as this one, but from a slightly different perspective, because here we look into tool states. And I'm not so sure how familiar you are with industrial engineering, but I think it's rather obvious what's being reported here. So every tool in a production line can be in various states. So it can be productive when it's actually producing something. but it can also be in standby. It can be in standby for various reasons, because there might be no worker operating it. There could be no product to be produced, but it could also be in a downtime because it somehow broke and it needs repair. And yeah, if we look at the state distribution in our manufacturing area here, we also notice multiple very interesting aspects. The first one is the time doesn't sum up to 120 days, which I think is something very exciting, but it's also something very scary, because it means that the data which was gathered and which was provided to us is not complete. Because obviously, I mean, all the tools should have the same amount. I mean, they're always in a state. They cannot be stateless. But it seems that some proportion of their time is not reflected in here. So somehow we don't get a full picture of what's happening. And for some tools, this is more present compared to others. But I think that's yeah, something to be concerned about. And yeah, in a real project, I would now go talk to my customers and ask them, okay, why don't we have full coverage of the time for all the tools? So all the tools should report the full 120 days, but they don't. Another example which we use to understand processes is time series. And I think, yeah, without going into any specifics about what's being measured here, I think we can nevertheless quickly discuss what we see here, because we have two tools, and both these tools produce metrics. And we see something which we very often observe in real world business processes, which is that the distribution is not constant over time, but the mean is changing. And we see that the variance is also not stable over time, but it seems to also vary. And in particular, in this case, in 2019, there seems to be a lot of movement, so to say, in the data, and it's unclear why this happens. And clearly, when understanding a process, when diving into the specifics of a process, we really need to, I mean, follow up on this, because this usually indicates that something is happening in the process which is not obvious from the picture, because in the picture nothing's changed over time, but we see a lot of variation and variability in the data. And a final example to give you some glimpse about how we typically start diving into process data is staffing. So what we see here is actually also from a real production area, but I cannot disclose which one, but it doesn't matter, because what we see here is different teams. So we have the teams S1, S2, S3, which work in the week, and we have two weekend teams, WE1, WE2. And what's shown here on the Y is how productive they are. So how many moves, how many items can they produce in one shift? And the shifts are displayed on the X. So there's a 6 o'clock shift, which then continues until 2 p.m. And then there's a night shift starting at 10 p.m. And this is, I think, a very interesting visual, because it already tells us so much about what's happening here, because obviously the shifts are not equally productive. They should be, and they are on paper. But if we carefully look, we see that there seems to be dramatic difference, for instance, between S1 and S2. So they seem to have a different level of, a different baseline of productivity. And what we also seem to see is that there might be some difference depending on what type of shift is being operated. So if it's a morning or night shift, they seem to be slightly less productive in S1 and S2 compared to the day shift. And also on the weekend, we see a similar pattern. It seems even more striking. So the WE2 team seems to be much more productive compared to WE1. And clearly, this would be another pointer where we may want to talk to our on-site colleagues, to our, to the workers and to the engineers in the process, to really understand what is the root cause. It's most likely not that the colleagues in WE1 are lazy, or usually they have other obligations which we are not yet aware of, which we would need to take into account as well when comparing shift performance. So these are the different, these are some examples for different angles where we look into the data. But clearly, as I pointed out, just doing data visualization is not sufficient. So that's why we then really rely on also a more statistical type of analysis to understand whether there are actually significant differences which we may want to also consider when modeling a process. So it's the same data as before, but here we just look at the S1, S2, and S3 team. And what we see here is some statistical analysis which we have performed to really work out whether there is a significant difference in team performance, in mean team performance, which seems to be the case here. But clearly, we also need to account for or consider the effect size here, which seems a bit low. So yeah, it still, I think, would require more research to understand what's impacting performance of the individual teams. So summing up the most important bits about process analysis. So I think one of the most important insights for me was that you should not just trust the bosses, but you should rather talk to the workers. And the reason is that everyone has a different perspective, and for sure, the closer you are to your business process of interest, so the better you know its specifics. So the manager might think he knows all about his area, but typically, yeah, there's always a different angle, there's different insights when you talk also to all involved parties. As we discussed, process description is, I think, the most important document in any simulation or optimization project. And I think to prepare it, I mean, it really takes a lot of effort. It's an iterative process. It really takes a lot of love to get right. And what we should always do once we have this process description is we should really question it and try to validate the documented processes based on the available data. And believe me, this is not a 1 week effort. This usually takes in real world processes sometimes many months to achieve, to just work out the process description, because I mean, in more complex processes, you have to do so many discussions, you have to do so much analysis before you really truly start to understand what's happening. All right, before we continue with the next part, for sure, feel always welcome to interrupt. If you have questions, if you have comments, I think, yeah, this, from my perspective, this is more also an open forum, open discussion. So if you have any questions, yeah, feel always welcome to interrupt at any time.
No questions so far, so I will try to monitor them, but nothing so far.
All right, sounds good. Okay, so then let's proceed. Let's yeah, talk about the next step. So we
okay, there is a question. Can you further explain V1 and V2? I did not catch what is the question about.
Can you elaborate the question a bit? Which slide are we talking about?
Yeah.
Here is this one.
Probably.
Yes, sure. Yes, it was a bit brief. So as I said, every panel here is a different team. So we have the team S1, S2, S3, and the 2 weekend teams. Weekend team 1, weekend team 2. And in this particular production area, they have a different shift schedule. So during the week, they do 8-hour shifts, but during the weekends, they do 12-hour shifts. That's why we see, I mean, generally a different baseline in the shift performance, because the weekend shifts work longer, they work 12 hours, which is not accounted for here. But nevertheless, we can still compare the weekend shifts between each other, and we could also compare the shift ID, so whether there's a difference between the morning and the night shift. But it doesn't seem that there's any striking or any difference at all between the morning and the night shift during the week.
Okay, there was another question which I do not understand, but I can read it. Maybe you will understand it. Can the data science work we do understanding our processes influence how we create our process specification, or do we purposely create the process specification first to sort of set constraints for ourselves? I'm not sure I clearly understand, but maybe you do.
I think that's a very good question. So I think both complement each other. So I mean, usually how we approach is, for sure, we talk to our partner, we talk to our customer. So they tell us some story. They tell us how they think their process is functioning. And they usually then provide us some data snapshots. So they could give us some shift data, the shift plan. They can give us some performance tables and whatever they have. And we dig through this data, and we try to align what we read from the data with how they explain their process to us. And very often there is a mismatch in the first place because they have some different mental model compared how their process actually is functioning. And I think this is also rather common because in complex industries, there's so many people involved, so that it's really hard to keep an overview. So I think what we do to answer your question is we really try to align what we, document in the process specification with what we see in the data. And we really try to make sure that those are in sync. And if they're not in sync, we need to dig deeper, we need to talk, we need to analyze more, just to make sure that we get a consistent picture at the very end.
Okay, I think the final question for now about the bottlenecks, if they are known in advance or they derive from simulation.
That's a very good point. Where's my bottleneck slide? Here it is. Okay, it's not so informative. Let's go to this one. So here we could potentially discuss it better. So I think, the problem with bottlenecks is that solving one doesn't necessarily make your process more productive, because what's happening very often is if you solve one bottleneck, some other bottleneck appears right away. So it may not help to buy another expensive tool instance, because then you basically shift the bottleneck one step further. And this is another very important application of simulation models, as we see later on, because in a simulation context, we can explore this. We can really answer, we can do capacity planning. So we can really ask the question to the model, what happens if I buy a new tool, if I hire another agent, if I hire another worker, another engineer? And we can also then really work out these what-if scenarios, which give us some indication if, changing the process in one way or another would actually allow to solve a bottleneck of a certain type, or whether the bottleneck would be simply shifted to some other process step.
We're talking, there is another short question. Is graph theory useful in this sphere? I think it is a short answer.
Yes, I love graph theory, and in particular when it comes to semiconductor, where, as I said, they have this very, very complex process routes with 1,000 steps. It's a cyclic process. So usually the wafers, they start somewhere in the fab, so there's so-called release of the wafer, and then they traverse the fab for months, and they come back to the same areas and same tool groups again and again. So I think graph theory is a very important means to understand routes here. It depends on the industry. For sure, if you have a linear assembly line, graph theory might not be the tool of choice. But if you have this very cyclic, complex semiconductor use case, I think, yeah, graph theory is definitely a tool. Does this answer your question?
I think everybody is happy, so yeah.
Then I'm happy as well. Wonderful. Let's proceed. So, all right, we talked about. All right, let's dive into the simulation part. So first, I would like to give you a brief definition of what we're talking about. So what is simulation? And as I will discuss on the next slide, there are actually different ways to do simulation. And we are just focusing on one particular type here, which is so-called discrete event simulation. And a discrete event simulation is defined as a tool that allows studying the dynamic behavior of stochastic, dynamically, and discretely evolving systems. And I think the discrete nature is of utmost importance here. So what's happening in discrete event simulation is that we have a system, which is our model, and it has some initial state. And then a discrete event allows us to propagate, to evolve its state. And then the next event is coming and it will evolve the state of the system again. And so what we have is a series of events which will evolve our state, but it's doing so in a discrete manner. So it's not a continuous simulation. There are also continuous simulation models which allow to model, for instance, physical phenomenon better. But what we study here is discrete event simulation. And you may argue that, yeah, this is quite a constraint, but in fact, you can model quite a range of systems and applications just relying on discrete state changes. And that's what we do here. So what are typical applications? We briefly touched on production planning, dimensioning came up in the questions. I think process automation is a very important aspect, capacity planning, but also project management. Okay. So in discrete event simulation, there are actually different, versions which have slightly different semantics. So the first, and I think that's also the most traditional way of discrete event simulation, is so-called activity-oriented, where you have fixed time increments, which are used to evolve your system. But this becomes very hard to realize when the number of simulation entities is increasing. Slightly better version is so-called event-oriented discrete event simulation, where you have scheduled events that are scheduled for some future execution time, and they will evolve the state of the simulation model. And finally, and I think this is what most frameworks are using these days, there's so-called process-oriented discrete event simulation, where we have a so-called vocabulary of interactions to describe the interplay between simulation entities. And we, in addition, for sure, keep a list of scheduled events ordered by future execution time. And when starting my work on discrete event simulation, for sure, I was looking around about what's there. So what simulation engine should I use? And there is already a lovely ecosystem, including many tools like Zimmer, Salabim, SimJulia, SimPy, DSO, and many more actually, because simulation is a very established field. And clearly, there's also other vendors like low-code commercial offerings like AnyLogic or Simio. But what I missed at the time was really some platform, some framework where it's not just the process specialist who can work with it, but where we can also onboard easily and use the expertise of software engineers and of data scientists. So I think this platform where we can onboard multiple experts coming from the process perspective, from the software engineering perspective, but also from data analysts, I think this is really what I wanted, but unfortunately, none of the tools really fulfills or my needs at least. That's why I thought, okay, maybe we should start something new, for sure, learning from what's available in the existing toolkits. And one very often occurring question is, do we have to do any coding at all if you want to simulate processes? Aren't there so many great no-code tools? And I think, yeah, there's a huge ecosystem of tools that allow to do all kinds of things without writing a single line of code. And clearly, simulation is also present here. So there's very nice tools like AnyLogic is a very prominent player here, where you can click together your simulation model. So you can pick sources, you can queues, you have generators, you can set all the properties, and you can run your simulation. However, in real life, these no-code tools, in my experience, they don't really scale and provide the techniques you need to handle and to model such a complex system. So in my experience, no-code simulation works in cases where the process to be analyzed, to be optimized is rather simple. But in more complex business processes and models, we need classical software engineering techniques to really handle the complexity of our model. So we need change tracking, like we want to version everything in a Git in a sensible way. We need to make sure that we can really scale the model to basically many processes running in parallel. We want to refactor our model. We want to, in the end, even run tests, unit tests, and CI/CD on our model. And from what I've understood is that most of, or basically all these no-code tools lack some of these requirements. So, what actually the one main motivation for me here is that we want to do process superposition. So similar to physics, where you have two movements which you can overlay with each other, I mean, as displayed here in this waveform, I think we have a very similar idea when it comes to business process modeling. So you have many very simple processes which are co-evolving and interacting. And what you want to do is you want to superimpose, you want to stack all these processes on top of each other. And clearly this becomes then a much more rich system compared to the individual process itself. And to establish such a framework where we can stack simple processes on top of each other, yeah, I started this process kalasim a while ago, which defines itself as a discrete event simulator. And it's really trying to achieve these aspects where no-code tools are struggling with. So it provides a statically typed API. It allows for dependency injection. It has some rather modern persistence approach. It does structured logging. It can be automated and so on. But nevertheless, it's designed also in a way that it becomes approachable for simulation practitioners and process analysts and industrial engineers. So what we do very often, we really do code reviews with colleagues who have no background in coding at all. So there have some very good experiments when it comes to logistics and line control. But thanks to the simplicity of how we can write simulations in kalasim enabled by Kotlin in the background, we can really also establish some means to communicate a simulation model. There was a question?
No, right now there was a question before, but I believe I can ask it now if you want. There was a question that the problem is close to system of systems. In that domain, there is a big focus on immigrant behavior, and the Johan was wondering if it's true here as well.
Yes, definitely. I mean, yes. I mean, you may know about the concepts behind system of systems, but definitely, because what we do is we can model processes independently, but then we basically stack them on top of each other to get some emergent behavior. So that's definitely a very important aspect here. Right. Cool. Yeah, and yeah, so I think this language perspective is very important. So it's written in a way that we can discuss it with non-technical colleagues, which I think is a very important aspect, because the process review and also the review of the more formal process description, and in one way or another, a simulation model is a very formal description of a process. I think, yeah, this review process is dramatically facilitated by using this framework here. But as I said, it's also really meant to be neither low code or no code. It's really code first. So at the moment, there isn't intentionally no real interface to basically click together a simulation model, because in our experience, it simply does not scale. It doesn't work for more complex models. All right. Go to the next slide. So yeah, it's all sitting on GitHub in case you're interested. So there's quite some examples. There's a test suite. It's containing different modules now, but I hope it's reasonably well organized to find your way. And nevertheless, I would like to walk with you together through what it actually provides. So it is a so-called generic process-oriented discrete event simulation engine. So what does this mean? What you do here as a modeler is you write down or you define simulation entities by writing a so-called generative process description, which defines the interplay with other entities. And we will do this in a second, so it won't be abstract. I just want to give you a brief overview about what we can do with it before we will dive into quite a few examples. And as I discussed before, what's very important here is that we provide good means to allow the simulation entities to discuss or to interact with each other. And finally, I think this is more technical thing, which does all the magic in the background, is we need the event trigger queue, which maintains future action triggers and which really drives simulation progress. So this is really a list of events scheduled for some future time, which then will allow to evolve simulation state. And finally, to understand what's happening in a simulation model, for sure, we need also means to introspect its dynamics and its state progression. So what's also baked into the API is monitoring and statistic capabilities. So what can we do with it? So I think foremost, it's for us and my colleagues and myself, a means to prepare a process optimization. So we talk to our customers, they want to improve their processes. So what we do is, as we discussed it previously, we model their process and then we assess planning improvements, for instance. But it can also be used for integration testing. It can be used for capacity planning, to study bottlenecks, and we also use it to do AI research. I will come to this a bit later. So let's look into a first example. So how does it actually work? How do we write a simulation model? So here on the slide, we see a first example, and it's about a car driving around. And how do we model this? So what we need for sure are the entities in the simulation, and every entity is modeled as a so-called component. So what we do, I hope you're now somehow familiar with the Kotlin language, but from what I understood, you had a very great lecture in the morning giving you some insights about what are the elements in the language. But for sure, feel welcome to interrupt at any time if the syntax is not clear or I should dig a bit deeper. So every car is modeled as a component. And as I just stated, in order to bring in the process here, what we need to do is we write a so-called process definition. So we can implement a Kotlin sequence, which implements the process here. And within this process definition, we can detail out interactions of this entity with other simulation entities, and we can work out and write down its life cycle. In this case, it's a very simplistic process. So what's happening for a given car is it will wait until the driver arrives. So it will request the driver, and then it will wait drive around for some simulation time until it reaches a traffic light, where it will then wait until the traffic light switches to green. Initially, our traffic light, let's have a look it up here, is initialized with red. So yeah, in this small program, it would wait forever at the traffic, at the crossing. But this is also just meant to give you an example. What we use here are all the three key types. So we have the component, this is the car. We have the resource, which is the driver, because the driver could be something which is sometimes not available because the driver is also busy in other parts of the process. So the driver needs to be requested. So we can request from a resource. And then there's the so-called state, which is the last main type in a simulation structure. A state can have a set of discrete values, and we can always basically wait until a certain state is toggled. And the process will wait here until the traffic light reaches green. To bind all these aspects into a simulation model, we can write down here that we want to create a simulation. We may want to enable some logging, and then we declare all the dependencies. In this case, it's the traffic light and the driver. We instantiate a car, and then we simply run the simulation for a couple of simulation ticks. So that's basically how it works. And what we see here are the key types, the components with process definitions, the resources, which might be something that is which is just limited, so it might be a bottleneck. And we have the state, which allows us to wait for certain states in a simulation model. And what we also see here are some of the most common interaction methods. So we see the request method to request from a resource. So this will also potentially stall until a driver becomes available. Then we have hold, which will suspend execution of a particular process for a given amount of time. And then we have wait, which allows us to wait for a specific state. So what's happening under the hood here? So let's look into this this event list, this future event list, which I was mentioning earlier. So when we have a process definition and there's a hold statement, what we do here is rely on the Kotlin coroutine library to suspend execution. So we really basically freeze the component when it's reaching such a hold line. We put it on the list and we schedule continuation of the component for a later point in time. In this case, it's scheduled for time 28. And what the engine is actually doing is it's really processing the list of future event triggers in an ordered way from top to bottom. So it will then proceed with the next component, which is scheduled for time 12 and will continue its execution. And once it's time for our component here at time 28, it will then proceed until it reaches the next suspendable point, which could be a request, because a request might not be honorable right away. So our process may need to wait until the clerk becomes available. And in this way, we can very nicely model and continuate processes at ease. So we will always suspend execution for hold, request, wait, and some other interactions. And the interaction engine makes, the simulation engine makes sure that these processes are continued whenever their time has come. All right, so we try to get some basic idea about how the simulation part works. What I also touched on earlier was that once we have a simulation, we need to analyze prediction accuracy. So we really need to compare the dynamics of our simulation model with the business process of interest. And how can we do this? I think that's also a very interesting question. It's a lot of fun to do so. So coming back to Westworld, yeah, for sure, some of you may have not seen it, but what's always a great part of the series is when the owners of these robots, when they try to study the robots and their behavior. So they always say analysis, and then the robot will freeze, and then they can basically explore the inner working and the inner mental state of these robots. And clearly in our case, it's a bit more simplistic, but the general idea is the same, because what we want to do is we want to study the simulation, we want to understand its dynamics, and we really do this by doing small what-if scenarios, and we discuss the outcome of our simulation with the process stakeholders. So what kalasim brings to the table to facilitate, oh, what's the name of the series? The name of the series, I think, yeah, let's stop for a second. I think that's an excellent question. It's Westworld. Let me share this one with you. Yeah, here you see one of the robots. And I try not to spoil anything. All I said about the series is happening in the first episode of the first season. All right, so I shared the link to the series with you as well. I have to bring this back. Wonderful. All right, yeah, so I think, yeah, understanding the simulation is at least equally important compared to understanding the process, because just if a simulation or a process model reflects what's happening in the real world, we can use a model as a means to make the process better. Because it's pointless to, for instance, assess how to use a better scheduler in a simulation model if the simulation model does not reflect the underlying process correctly. So what kalasim brings to the table to facilitate this process are various tools. So there's so-called event log. So we can always trace the series of events that has helped to evolve the simulation state. They are built-in monitors to track state and statistics of all the entities like states and components and resources. There's lifecycle records that basically really summarize what's happening with the component. And there's also built-in visualization tooling to also understand and to study the spatial temporal dynamics of the simulation entity. So what we do very often is we run simulations, sometimes also at scale, like we run hundreds or thousands of them, and then we export the metrics. And in Kotlin, this is extremely easy, because whenever we have a list of something, so whatever could be an arbitrary type here, we can always rely on reflection to convert this into a data frame, like you may know from pandas or R. And then we can write this into a file and study it in whatever EDA framework we love, could be Excel, Python, R, or maybe even the Kotlin kernel. So I think that's a very common approach we use here to really get the time series produced by such a simulation into our favorite analysis tool of choice. And using this approach, we are actually pretty successful modeling various manufacturing processes in my case. So we can really model production areas. We even have modeled entire factories with this. And we can really study and use this model to suggest and to prepare process improvements. So just to give you an example, so this was one of the production areas where we are currently working on. Names and tasks are redacted, but nevertheless. So we try to simulate an entire area, and we also don't account for just the products being produced, but for sure we also account for supplementary processes, in particular tool maintenance, because in most complex production processes, there's a lot of maintenance going on, and to properly understand the dynamics in such a process, you also have to account for them. So what we did is we simulated a bunch of supplementary activities that contribute to tool health. And then we can for sure visualize the maintenance schedule here. So we have the dates, we know when Friday and when Monday morning is. So we can really take this and confront the process owner with this view to really assess if what our simulation has calculated reflects what they also observe in their real process. One way to do this is for sure, as I said, to export the data into R or into Python. But as I said, you can also simply run this in a Jupyter notebook. And I wanted to share a quick example how to do so. So it's very easy, actually. So like in every Jupyter notebook, we first basically declare the dependencies we want to use. We then import, because it's a Java program in the end, what classes to use. We then define certain constants that configure our model, and then we can implement the individual components, the different key players in our simulation model. And this type would be car. We can bind them all into a simulation object, and then we can run the simulation directly in a Jupyter environment. All right. Before diving into the first exercise block, I want to highlight one other aspect, which is process animation. I mean, clearly analyzing data using statistical and exploratory means is one way, but since simulation models are often very complex in nature, it's sometimes hard to visualize them with classical tools like box plots and time series and so on. So what practitioners very often like to do is to do process animation. So they would like to take their process simulation and superimpose some kind of rendering framework to make them more visible, and if possible, even doing this in a way where the user can interactively play with the simulation model. And luckily, there's a wonderful project for Kotlin. It's called Open Render, and it defines itself as an open source framework for creative coding. So it's written in Kotlin, and it's really designed to making real-time interactive software development very easy. So what I did is I looked at it, and I was really amazed by what it can do. So I started working out a small support API where we can take a complex simulation model and superimpose a simulation on top of it. And just to give you one example, I would like to actually run a simulation together with you. It's a simulation of an elevator. So let me bring it back to the. So yes, and before doing so, let's briefly walk through the simulation, through the code itself. Unfortunately, it seems that my IDE needs some time to come back. Let's kill it. That's not good. Give me 1 second. Sorry for inconvenience. Move this one. Oh, my computer is a bit slow at the moment. Not sure what's happening. Okay.
Zoom happening.
Maybe, yes. This. Yes, all right. Okay, so let's look at the code first. so that you can see also a more complex simulation, and feel always welcome to interrupt, elevator. Let's try whether I can use some of the fancy presentation modes here. Oof, I don't do this so often. So what do we use here? View, code. I know that there are some
appearance, view appearance presentation.
Presentation
and the
mode.
Presentation mode. Yeah.
Yes, here it is. So now it is, yes, I think that's much more eye-friendly, in particular when you're sitting elsewhere. So let's walk through a simulation which is meant to model an elevator system. So let's pretend that we have a big skyscraper with I don't know how many floors, and we have a number of elevators, and they are supposed to transport passengers. And what we want to do is we want to do a capacity planning. We want to know how many elevators do we need, what capacity should they have, what are expected arrival counts, so how many passengers do we expect. So this is basically the business problem or the business process which we try to model here. And we can write down this rather easily. I mean, yeah, it's all sitting in this file. It's around 200 lines of code. And I don't want to dig into the details. I just want to give you a first glimpse about how to model this process with kalasim here. So first thing we do is we simply declare some object, some enum, to model directionality of a moving of an elevator. So an elevator could be going down, up, or could basically hang around at a certain floor. Then what's very important is we need to create passengers. So here they are called visitors. And in such a context, all we care about when it comes to a passenger is at which floor do they start, and at what's their intended floor where they want to leave the elevator. So what we do here is we basically build some kind of sequence where we have random controlled sampling of floor ranges, where the visitor is starting and where he's heading to. And most importantly, as I discussed before, there's a process description. So we really need to model also this visitor generator. So it also has an associated lifecycle description. And what it's doing is it's simply forever sampling a new from two pairs, so a destination and a target. It's instantiating a visitor. Then it's basically going to sleep for a certain amount of time, and then it's creating the next visitor. The visitors themselves are for sure one of the key entities in the model. So they have a floor where they want to start their journey with the elevator, and they have a target. And what they do here is they pull certain elements from the environment. So we use some dependency framework called Coin here, which is a very popular dependency injection framework in Kotlin, to bring in elements from the simulation which we may want to use here. And what we do here is we know from where the visitor is starting and where he's heading, so we can resolve those numbers into actual floors, and we can also figure out its direction. And with these elements, we can then write down very easily the life cycle, so the process definition of each visitor. So first, what he does is he's queuing up in line because there might be others waiting at the same floor. And clearly, if nobody has pressed the button, he will press the button depending on the direction where he's heading to. And finally, if none of the elevators is active, we activate them. So we basically make sure that their process definitions are running. And then all we can do here is wait, because then it's basically up to the building to send an elevator to the floor so that the visitor can enter. What's also equally important, and these are the workhorses in the simulation, are the elevator cars. So basically these small wagons that go up and down. And here the process is more or less the same. So we have a couple of visitors which are sitting inside of, or which are standing inside of each car. And then there's also associated process definition, where we have a directionality, visitors are coming, going, depending on the floor, it's moving around. Everything takes time for sure, because the movement of the car takes time, opening the doors takes time, closing, exiting, entering passengers, all takes time. So we write down this process. And my point here is actually that we can do so, and we can also analyze statistics and metrics of this process. But in the end, even with this, I mean, rather simple model, it becomes complex very quickly. So we may need to do quite some reading and also quite some debugging to make sure that we get the process dynamics right. And this is when simulation, when animation becomes very important. So let me show you how we can simulate this process. And now I have to get rid of this view, navigate, view, appearance, exit presentation. Wonderful, because then, yeah, we can, I mean, for sure we can run the process. Let's do so. Basically, using standard programs. So we say we want an elevator, we run it for a certain amount of time, and then we simply print its metrics. So let's do so. It's very quick to do. So just to get a vague idea, but as you will see in a second, yeah, but just looking at the metrics, and it would not help to visualize them in R or Python or whatever. I think it's very hard to understand what's happening here and if we model the dynamics correctly. So what we need to do is actually or what we could do, and that's what I'm going to present in a second, is we will use this animation on top of this simulation model to really visualize the processes which are happening here. All right, and for sure, whenever you need it, the compiler is very slow. So let's give it a few more seconds to do whatever it wants to do. And in the meantime, we can check whether there's any questions, but there aren't any. So let's wait. Here it comes. Very good. So now it's spinning up the simulation as we see it here. It will run it, and after it's complete, it will simply go through the floors and print out some metrics. Okay, so this is what we get. So at the basement, we see quite a huge line. So there's 1,200 passengers. No, here 1,400 passengers, and yeah, the other floors, I mean, don't have so long queue. So obviously, our capacity planning still needs a lot of work here because we have queues stacking up and getting longer and longer. So let's use our animation model on top of this simulation to understand and study process dynamics. So as I said, it's built using Open Render, and it's extremely brief. So it did not take much time and effort to build it. So all in all, the entire simulation is, I think, yeah, not even 300 lines of code. And what we get here, where is it? Here it comes, is this type of application where we see the individual floors, we see passengers showing up, they have to wait, they indicate the directionality where they want to head to, and then we see the individual elevators, including their current visitors, moving around and delivering the passengers to their target floor. And what we can do now here is we can do very easily some interactive capacity planning, because we can now really adjust all the main settings of the simulation model. First, for instance, we could increase the number of floors very easily. So we make it like we would have 20 floors in our building. And then we could play around with the number of elevators. So we could say, okay, maybe there's just one, because elevators cost money. So would it be sufficient to just use one elevator? We could run it for a while, but as you can already see, this is unlikely to work because we already see the queues starting to fill on various floors. So this is unlikely to work. So let's just increase it a bit. Let's say we want to play 4 elevators, and maybe it's more efficient to reduce the capacity of them. So we could use, for instance, 5 cars with a capacity of 2, or we increase it a bit and reduce this. And most importantly, for sure, we can also address the generation abilities of the system. So we can modulate how many passengers will actually arrive here. And to make it a bit faster to analyze, we can also adjust the time. And then we can interactively study whether the processes which we have baked into the simulation model are working out as intended. So it's not just the capacity planning tool which we are looking at, but it's also a means to debug a complex process model. All right, now let's close this. Let's jump back to the presentation. And so we talked about this. Exactly. And now I think it would actually be good time to do some analysis together. I'm not sure whether you did some. Oh, there's a question. Is it possible to use kalasim instead of formal methods? Let's bring this one to the main screen. Mirko, could you elaborate the question a bit? What do you mean with the formal methods?
I mean, I think you meant the analytic methods.
Oh yes, sure. Yes, okay. Let's to answer your question, let's do something different. Before diving into the yes, for sure you could do game theory. I mean, it's actually very easy to do so. And in the repository, you find quite a few examples from classical game theory and scheduling theory already being worked out. To answer your question, Mirko, whether we can combine it with some more analytical approaches, let me show you one more example. I mean, I could also leave it to you. So would you rather want work through one more example, or would you prefer to work on some exercise block now? Let's do the one more example. I think it's a lovely example. It's one of my favorites, actually. So let's jump back. So it's about the Lunar Ice Challenge. So what the heck is NASA's Lunar Ice Challenge? It's some initiative from NASA to mine ice on the moon. And this is one of the design concepts which they have created. And the idea is that this bubble in the middle is actually melting the ice underneath it. And then they want to transport the water to some base. So they have some, they published some maps. So this is somehow the moon, and then they have the distribution site, and they have the mining area. So these robots actually have to move around, as you can see here in the picture. And I really love the example. There's also a couple of links embedded in the presentation if you want to follow up here. But it's really a great project. And I thought, okay, this looks exciting. Can we model this? So because obviously there's a couple of things which you may need to plan carefully, because bringing stuff to the moon is very expensive. So they, for instance, may want to adjust the number of mining robots. So I basically worked out their idea and pretended, and it was also a fun exercise because it's one of the examples in the repository, that there's an Earth Space Agency, the ESPA, and they wanted us to work out a simulation model for the process. And the idea is that in this process, there's some kind of base, and the base must be supplied with water. And what they want as an outcome is some capacity planning. So we want to know how many robots do we need to gather water ice. And we also want some forecast about production KPIs. So how much water would we produce with such setting per day? So to work out this example, I mean, it's all made up. I mean, I just took the Lunar Ice Challenge from NASA as source of inspiration. But what I thought, okay, what are realistic assumptions about the process? So that's what I came up with here. So first, there's a rate limited process. So everything takes time: transport, search for water ice deposits, mining. And what we could also assume, I think, is that the specific locations of the ice deposits may be unknown initially. So maybe we know the average distribution of deposits on the moon, but we don't know where they are. And what we can then try to model is this idea of this harvesting process, that we have some kind of base where we deploy our harvesting robots, and they will scan the surface for deposits. And once they find it, they will try to mine it, deplete it, and bring back the cargo to the base. And clearly, each miner has a limited storage capacity, so they will need to constantly shuttle to the base. And also, the base will consume water constantly. So just to make it a bit more fun, so they will use water because there's some cosmonauts or astronauts sitting in the base drinking water all day long. So we need to make sure that the base doesn't run dry. And clearly, at the beginning, there's some initial amount of water deposited at the base, just to make sure that the cosmonauts don't die at the beginning. Okay, and what I then did is I modeled this process with kalasim, and we can use the IDE build and visualization abilities to also simply visualize the API surface of the model. And I think it's rather easy to read, because all we have is a base which does some negotiation regarding search and deposits, and it's doing some assignment of harvesters to certain deposits. We have the mining robots, which can be in searching mode, harvesting mode, or unloading mode. And then clearly we have a map with initially unknown deposits, which are basically modeled as using some position and capacity. And all these elements are then bound into a simulation model called Lunar Mining, where we have a list of harvesters, a map, and the base. And the way we write down process definitions is exactly the same as we discussed previously. So we simply write down what's happening. And some of these steps, they will stall process execution. So we will rely on Kotlin coroutines, for instance, in this hold operation, to freeze the component, put it into our event queue, and continue execution later on. So what we do here, for instance, in the unloading is we move to the base, then we unload the cargo, we put the cargo into the refinery of the base, and then we activate another process, which is a harvesting process. And so coming back to your question, can we combine this with an analytical approach? I would love to show you an animation which I have created using this process, and we can actually, we could run it from here. So let's start here. So it's basically also an animation on top of this simulation model, where we model the process dynamics with Open Render again. So now we can really understand what's happening, even without digging through the code, without reading all these process descriptions. So we can really visually validate and ensure that our model behaves as intended. And what we see here is the small mining robots. I mean, first searching for deposits, then they mine these deposits. So the deposits will shrink over time in size. And once the deposit is depleted, the robots will start scanning the surface again until they find a new deposit like here, and then they will start depleting it. And the base is also supporting this process by providing deposit assignments to the to the robots themselves. And clearly, animation is here just one part of the picture, but we can also use the same model in an interactive Jupyter environment. And I did so here. So let's look at this example. Let's make it a bit larger so that you can read it more easily. So what we do here is we use the Kotlin Jupyter kernel. We load some libraries. Essentially, we just load kalasim and a visualization library. And then we can create a couple of simulations. And to make it even more fun, we don't just run one simulation, but we vary over the number of harvesters. So we say we want from 1 to 9 harvesters per simulation. And then we simulate each configuration 100 times. Because in order to do capacity planning, we cannot rely on one simulation run, obviously. So we have to run it again and again to make sure that we get solid numbers at the end. So we do so, we run the simulations, and then all we have to do here, and here comes the analytical part, is we pull out the metrics, and we can do this, for instance, like here, we take our simulations, and then we simply extract certain properties. In this case, we extract the number, the water deposit size at the base. And once we have pulled out this water at the base, we can rely on some visualization library, which we do in place here, to visualize the progression or the evolution of the water supply at the base over time. And since we have simulated not just one configuration, but we simulated different runs with 1 up to 9 harvesters, we can see very nicely how the water amount at the base is evolving. So for sure, always at the beginning, it's decaying because the base is consuming water. So it takes some time to find the first deposit and to start mining it. And clearly, the more harvesters we have, the faster we may find a deposit. What we also see here is that in some configurations, like with one harvester, we have quite a few simulation runs where the base runs dry in the long run. And clearly, this is something we want to avoid at any cost. So you would have to pick some other configuration. From this picture alone, I think it might be hard to see how often the base runs dry. So we can take the same data and simply work out the number of runs, simulation runs, where the base is actually running dry. And what we see here is when the number of harvesters is increasing along the X, the number of simulation runs where the base is running dry quickly decreases. So maybe picking or shipping 5 harvesters to the moon would be a good number. I mean, it's not certain that our astronauts won't be thirsty, but at least, yeah, I think we have very favorable odds then. So I hope this answers your question, whether we can use the same simulation model along with an animation as a component, but also analyze it using more traditional data science tools like R or Python or Kotlin in parallel. All right. Yes, and now I think I have talked for way too long. I would love to do an exercise together with you. And actually, it might be a bit hard to do so, but let's try it nevertheless. So the way I thought we could try it is I have shared a notebook, and let me try to bring you all there. And I hope this works. If not, we have to do it differently, but let's try. So I have the Zoom chat. So maybe, yeah, and I need some feedback from you. So let's open this workbook. So what should show up is an interactive kernel environment.
No, since you shared the read-only, each one who wants to work it in the interactive mode, they need to create their copy. It's okay.
Okay. Wait a sec.
So you can share the link where people can follow what you do, but I believe you can't share a link that people can do themselves together with you, because for it you need to pay the account, and I'm not sure about the number of connections.
Okay.
But
so let's try. So I can try to share this. And what type would you recommend?
View only, because you can't do anything else with a free account.
Okay. So,
and people can follow what you are doing.
Okay, let's try that. So let's share this link with you. I think the first link was wrong. So let's try this one. Okay, let me try to open this myself. So what you should get is some view which looks like. Exactly. This is what you should actually see. Oh, I see lots of views here. And now I think, yeah, you should not edit this one. I think this is not what I intended. So the idea is that you create your own copy, but I don't know whether I did it right.
Yeah, we can do a clone to, there is a button there to clone to our own home. So we can do it. It's okay. You do not need any other link.
Okay.
And people can just look into your screen and copy to and practice in their own notebooks. It's fine. The only thing that is not copied, we checked recently, is the data attached to the notebook. If you have something, it would not be copied.
Yes. So maybe. So what would be the? So you would do tools. No. So how would you copy it? Let me try this.
No, it's okay. You do not need anything else. You just start working here, and people can work in their own copies. So.
Beautiful. Okay, so let me give you a start. So what do we do?
For those of you who did not understand, you have this orange thing on the top, clone to the home folder button, and you can press it and open your own copy of the tutorial, and you can play around with it.
Yeah, so I think I somehow shared it incorrectly, because I still see lots of cursors here, which I did not expect. I mean, I don't mind them, but I did not expect them. Okay, so let me give you a brief intro into the example, and at the bottom of the example there are a couple of questions, and I think that's where we could take some time to dive a bit deeper if you want to, but we may also not I mean, manage to do them all today together. So what do we do here? So it's an interactive environment. It's similar to Jupyter, if you're familiar with that one. And what we do first is we simply load required libraries. So we simply can play press the small play button. So what it will do is it will try loading one of the libraries, and yeah, usually it's quick. Sometimes it takes a bit longer. And once we have loaded them, we can then doing the imports. So we can import all the methods we want to use. Okay, so I think many of you are working in my notebook now, which makes it a bit harder for me to navigate. Anyway, so what we do here is we simply simulate the model which we discussed earlier. So we see this car model. So we have the driver, we have the traffic light, we have the car component, we have its process definition, and then we bind everything into a simulation model. And once we did so, we can simply run the simulation model. So we run it for a couple of seconds, and then we can start analyzing its properties. So we can, for instance, display the claim timeline.
People also asking to increase the font size, so maybe just increase something like that.
Sure.
So they can be.
I somehow lost track of the chat. Yes, you're so right. Thank you. Okay, I think we still have many of you in my notebook, because
it's okay. They can just in the two separate tabs, one for your notebook and one for their own. So it's okay.
I see. Okay, wonderful. Yes, and what we can do once we have run the simulation, we can then start analyzing its process dynamics. So what we, for instance, could do, we could analyze the driver, and as we discussed, the driver is a resource. So it's a limited element in our simulation. And what we see here is that the driver is claimed right at the beginning, and then it's never released. So our one driver seems to be in 100% use throughout the entire run of our simulation. What we could also do is we could pull out some statistics of our simulation as a data frame, so like as a table to study. And what I did now here is I wrote down a couple of questions just to get into a discussion with you. We may not need to do them all, but I think, maybe I could give you a couple of minutes to basically try playing around with the model and trying to get started with one of these questions, maybe, just so that you get some better idea about how the modeling part works and how to work with the API. And I would clearly then try to work out some of the solutions together with you. When doing so, I think we also would need to look at the schedule. So what's the schedule for this afternoon? So we should, I guess, do a break somewhere. What would be your recommendation? Maybe Anton, maybe you could help here.
Sorry, I was out. If you was a question to the auditory, could you repeat it?
So I was just asking whether we should do a break somewhere.
Oh, it's up for, I believe it's up to you to decide. I'm not sure. Organizers are not answering, but people do not ask for the break, so I think it's up to you.
Maybe we could do it like this. Everyone does a break now, or if you don't need a break, you can simply start working on the exercise, and then we all come back in, I guess, maybe 15 minutes to discuss some of the solutions. How do you feel about that?
I think it would be good.
All right, cool. So let's continue. It's now I have to do Moscow time. I think it's 4 o'clock and 10 minutes now. So let's continue here. When is it then? 25 past 4. Okay. All right. And if you have any questions, meanwhile, Anton, you mentioned that we could also have breakout rooms here. I'm happy to answer your questions meanwhile for sure. Or if you need support with this data lore, with the interactive kernel environment, feel also welcome to let me know.
Do we need a breakout room now?
I don't need them, but if some of you are a bit more shy and don't want to discuss their question in front of the complete audience, we could do them. I don't mind. All right. So yeah, I will pick get a coffee, and yeah, let's be all back 25 past 4. And yeah, if you want, you can now go together through some of the questions, or what would be your preference? Anton, what do you think?
I'm sorry, what was the question?
How we should proceed now. Oh, there was one comment from Johan. We should go through the exercise parts. Very good. So we still struggle with data law, so the platform seems to be a bit slow. Not sure whether it's because of the number of parallel users or whether there's some other problem with it. I don't know.
I think it's your decision to make. If it doesn't work, maybe there is no point in proceeding.
Let's try. The only thing I would like to ask you, could you stop running cells in my copy of the notebook? This would make it a bit easier for me to navigate here. All right. I mean, feel always welcome to create your clone the workbook, or to create a copy, or just keep it open, but maybe not run anything here, because then it's a bit easier for me to work around. I mean, to navigate. All right, so let's simply start. So first thing, how can we recreate simulation and use a simulation type? So what does it actually mean? So if we go back to the simulation, we see that we create a simulation. In here, we create dependencies, but what we get back then is a simulation which we can run, but we cannot easily, for instance, obtain the car. So if you would want to do something like, let's do another cell here. So let's make sure that this is all executed. Run, yes, it runs. So let's make sure that it's the current stage. Okay. I think the dependency loading always takes a bit, but not sure why actually, but okay, now it's getting there. Okay, so now to prove my point here, so we can run the simulation. This works, but what's still a bit tricky is we cannot pull out the car. So we could try that, but this will fail miserably, because yeah, if you know a bit of Kotlin, I mean, there's no way you can extract the car from here, because yeah, there is simply no way to obtain a reference. And I think this is a very common scenario, that when building a simulation model, yes, unresolved reference, exactly. So that we want to also introspect its components. And as pointed out in the this is a hint here, if you go to the documentation, so there's a website for the library, it suggested, you could read for it later, that instead of using this create simulation, use a dedicated simulation type for the simulation. So we really say we want to create a so-called simulation environment as a type, which we then instantiate later. So, and we could do this as we will simply rewrite our, I have 2 copies of it. We will simply rewrite our example accordingly. So let's try that. It's actually very easy. So we simply say, so we put this down here, and we say we want to create a class. It could be, let's call it traffic, for instance, and it is of type simulation. And and within here, we could then initialize its component. So we could now declare, because this is a regular Kotlin type, we could also declare reference to our car. And later, when we want to build a simulation, we simply instantiate it. So we can now do this. We run it. Let's see how it goes. Yeah, data law is still a bit slow. Okay, it says expecting member declaration. Why the heck is that? Maybe I messed some brackets up. No, let's split up split cells. Split. I think that you can split also the cells here. And let's try to run this part first. Okay, so we first just declare what's needed in our simulation in terms of entities, like we want to have a driver, traffic light, and a car. And in the next step, we actually work out the simulation. And what we could do here is actually, because we want to study also the other guys, we could also assign them here, traffic light. So we do two things in parallel. So first, we declare this as a dependency. So whenever we want to use it to refer to the traffic light, we can use the dependency, the coin dependency solver, to pull it into an entity context, for instance. And secondly, we assign the traffic light to a variable. So later on, when working with our traffic instances, we can relate very easily to those elements. So let's try to rerun this bit. And now it worked. And now we have the simulation, or somebody else is still working in my notebook anyway. And now we can run the simulation. And now we can also extract car. So we now have a direct access to the elements. And within the, because it's a statically typed language, we can then also assess properties of the car. So we can use code completion, which seems a bit slow here. Okay, I still think the data law is a bit slow here. Yes, and now we can still use this, but we can now also directly access the driver, because now we use a type construct. So we really have a variable driver within our simulation environment, and now we can use this. I think it's in reactive mode. I think that's the problem. Okay, I don't want the reactive mode for now. Now it's restarting the kernel. I think the reactive mode is actually a nice feature, which always makes sure that it keeps the cell outputs up to date. But depending on how you work with it, this might not be always a good choice. So now I disabled the reactive mode. Now it seems to restart the kernel, but then I can work with this more easily. All right, so I think this was the first step. So we managed to do this. So we have written this create simulation to use a dedicated type for our simulation model here, in which we can now have use all the power of Kotlin to declare what we want to do. So if you would have some constructor code, you could easily put it in here. We can declare variables and so on. And with this type, we can instantiate an instance of a simulation easily here, and we can run it, and then we can also access its properties more easily. All right, so what's next? So let's look into the second question. So the second question is about how can we toggle the traffic light, and maybe you can help me with that. So I for sure know the answer, but I think it's also very good that we talk about it. So what would be your suggestion? How could we model the traffic light in a better way? Do you have any ideas which you may want to share here? Okay. Rahim, please go ahead. How can we do so?
Can we use the event queue to do this, and we can schedule an event in order to?
Yes, for sure. It's all event driven. I mean, and that's a very good point. And we sometimes may not even see the events, but everything which is happening here is triggering events internally. So the request will trigger an event. Hold, wait, they're all event-based. And the question now is, how can we model the traffic, work out the traffic light better so that it's actually turning green somewhere? Because in our current model, it's never getting green. So there's a suggestion. Do you see the chat window when I move it to the main screen, or is it something I can only see on my end? Okay. Anyway, so in the chat, Chizomo said we could potentially use hold and suspend for some minutes. We could do so. We could try to use hold and suspend, but actually what we don't want to, we want to write down the process of the car in as simple as possible way. So what I would actually suggest is we add some new component to our model. So we could say we have a traffic light controller, which is another component. And clearly it needs a reference to the traffic light to modulate its state. So we can pull in a reference and then we simply do the same as we did here. We work out a process definition to control the traffic light. And how do we do so? Yeah, so depending on the state, we may want to toggle it. And if we don't, and in between, we always may want to wait. So we could say that until eternity, what we would love to do is we want to wait for 2 time units. Oh, data law says that my machine is running out of memory. That's not good. And now I have to buy it. Okay, let's ignore this comment. And can I type? Yes. And now we what we have to do is we have to check the current status of the traffic light. And there is actually the value of the traffic light. And if it's red, we make it green. And else we make it red. So, and to make sure that the simulation picks up the additional entity, for sure we also need to put it in here. So, I mean, what we could do is we could simply instantiate it, but in case we also want to analyze it later on, we could also assign it to a variable. So with this, we now integrated the traffic light controller into our simulation model. And to assess the improved dynamics of our model, we would now need to re-execute this code block. There seems to be some problem. Unresolved. Okay. Somehow the yeah, I had restarted the notebook, so I have to reload the library again and run the code bits. I think this happened when I disabled the reactive mode. All right, I think, yeah. So now it seems to be super busy with 97% CPU usage. That's a lot, given that I just want to load the dependency. But now it's making progress. So now it has loaded the libraries, and now it will compile internally the entity classes. And I guess for some of you, this might be a bit odd. So what's happening here? What is this value thing? But again, I think there, if you're interested to learn more about it, there's documentation. There's an entire section about state. So here we discuss how to set the values, how to wait for it, how to use other variations of state. So clearly we don't have to use red as a string only, but what we can also use, we can have numeric states, or we can have typed states that, like, you could also use in enum to make it a bit more type safe, because what we do here at the moment is actually a bit messy. So in a real simulation, I would never work with strings like red and green, but we could use declare an enum instead and use the enum value. You have raised your hand. I couldn't pick up the name. But
yeah, I think it's me. Yes, I think you have an error with 2 equal signs.
Oh yes, thank you, thank you. That was today. So yeah, I think I would have noticed a bit sooner, but thank you for pointing out. Yeah, indeed, if we want to check the state here, and depending on the current state, we want to toggle the state. And now, yeah, we can bind it all together, instantiate a simulation object, and then we can run the simulation object for 5 ticks. And now what we could do, let's really inspect what the controller is doing. So now we have the controller. I wonder why we don't get any completion here. Ah, yeah, status timeline, and then we try to display it. So now what we now try to do is we pull out the status timeline of the controller itself, but for sure that's not really helpful because it's scheduled all the time, which makes sense because I mean technically when you install execution a component, it's basically scheduled. It's not waiting for something, it's simply suspending execution. So what we actually are interested in is not the controller itself, but rather the progression of the traffic light itself. So let's ignore the controller and let's rather look into the traffic light. So what can we do with the traffic light? The completion is, yeah, I already talked about this in the breakout room. Usually I do this in the IDE where the completion is still a bit better. So metrics. So we have the value monitor. Okay, unresolved. Okay, there seems to be some problem with my statement here. So let's see whether I can get this one. It's already takes way too long. I think it's because my VM, which is provisioned by the platform, yeah, is somehow busy with stuff. Okay, so somehow doesn't like this part, which is a pity. Compile sync. Yeah. Great. So yeah, somehow the completion is not this. Yeah, okay. So I think this gives us some indication, even if it's not that pretty. So now we can do a histogram of the state of the status state variable, and we now see that it's actually nicely switching its state. So we could also run the simulation for longer and redo that. So let's check again. Yes, we see after a while it's now perfectly balanced. So we could now solve the second part. So we could introduce a traffic light controller to modulate the status or the value of our state variable. So there was another question. Why is the driver busy until the end of the simulation? So do you have any idea? I think this is kind of obsolete because initially we were waiting in front of the red traffic light and it was never turning green. But now, since we have added our traffic light controller, the driver will actually be released from the car after it has passed the traffic light. So we should actually see this. So when we look into the driver and redo the display, it should actually, yes, now we see this very nicely. So it's busy just at the very beginning of the simulation until the process definition has ended, because as we modeled it up here, we drive, we wait, and then we are done with the process. There's no follow-up. So basically this component becomes idle and we release the driver automatically. So this answers this question. Yeah, the next task was to add a driver generator. And if we look into our simulation, it's a bit dull and a bit boring that we have to instantiate one car and then, yeah, basically there's just one car. And I think that's not a realistic scenario. But what we instead would like to do, I guess, is we want to have a continuous influx of cars which are driving around. And one way to do so, and I think this was also pointed out in the instructions, was we could use a so-called component generator. So we could use a simple component which will take some arrival distribution. So this is the controlled randomization thing where we have where we can also replicate the run of a simulation perfectly. And we use this controlled randomization, for instance, using exponential arrival distribution to create new cars. And clearly, we could easily add this to our simulation. So we could simply go here and say, okay, in our simulation, we want to create a component generator, which needs to be parameterized. So we could say we want on an average an exponential distribution with a mean of 4. And clearly, we don't have customers which we want to create, but we rather want to produce cars in here. And what else in the list? Feel welcome to ask any questions if something is not clear. So yeah, and as you can imagine, with this new approach, with the car generator, we now definitely will struggle because our model has too many arguments for exponential. Okay. We will definitely now struggle with the resource because as we modeled it initially, there's just one driver in our simulation, and clearly, if we have, I mean, more and more cars, this doesn't really work. So what we could do is we could increase the capacity of our resource. For instance, we could say we have 4 drivers. So if it's something like some kind of taxi business, for instance, yeah, we could hire more staff to make sure that we can all keep all the cars in motion. And I think now we are working our way through the list. So we talked about the drivers. We talked about, this is for sure not drivers, but a car generator. And yeah, how can we study what they are doing? I think we already did the first thing. So we looked into a particular driver, and clearly we could also use other slots of the driver, which we could always look up in the documentation. So every resource has a couple of statistics endpoints, which we could use to study their claim timelines, the capacity, the occupancy of the resource or its availability. And the last question was, how can we ensure that the car is regularly maintained? I think, yeah, that's another interesting question. And typically what we would do is we would simply add another process, because I think that's something which we can add very easily. We would add another process where we make sure that every car is pulled into maintenance once in a while. But I would leave this as an additional exercise for you. All right. Do you have any questions regarding this first example? I mean, I'm aware it was rather brief. We didn't have much time to go into it, and clearly to understand properly how to operate such a simulation API, we would need a bit more time, like a day or two, to really work out the examples with a bit more love and in a bit more detail. But nevertheless, there was a question. So the question is, what is the RG in the exponential component generator? That's a very good question. So where is the RG in the component? Yes, so let's remove it. I will explain in a sec what the reasoning was. All right, so actually this is sufficient. But nevertheless, I want to answer the question. So the question was, why was there an RG initially? And it all boils down to controlled randomization, because the simulation is always also a randomization experiment. So we will need to put in a controlled amount of randomness to study model dynamics. And clearly, as a designer of a model, we want to do this very carefully. And by design, simulations in the framework are totally deterministic. So there is actually nothing random about it. So we can rerun even a complex simulation like of a factory or whatever, and we will get exactly the same outcome, unless we set a different seed. So with this, we can really instruct the random generator to behave differently, and then we can also explore different trajectories of our simulation model. And coming to your question, in previous versions of the library, you could provide the random generator as an argument to various continuous distributions which are supported by the library. But this is actually now more convenient because the library has been improved more recently, so that this is no longer necessary. So it will automatically infer the random generation from the simulation environment when doing this. So all we have to do here is we have to provide the mean value for the expansion distribution. All right. So are there further questions regarding the examples? Clears it out. Very good. I have a question to you, Anton, or to the organizers and journalists. How much time is left? So I have a few more slides to sum up the topic, but I also have some additional slides in case there's interest regarding optimization. So what's our timeline for today? I can't hear you yet.
I think you are supposed to finish at 17:20, so it's 25 minutes yet.
That's perfect. That's exactly the time I need. Wonderful. Thank you. All right. Yeah, summing up the exercise, I think we explored an interactive kernel environment using the traffic exercise. It's all based on Kotlin Jupyter. Also, data law is based on Kotlin Jupyter, as far as I know, which I think is a great tool, but it also still is a very young product as a kernel, and it still suffers from actually quite a few issues. So, I mean, I think it's good for teaching to get started with the library, but quite a few very important language features are not available yet in the kernel and also not in data lore. So personally, when we do method or model development for our customers, we exclusively use the IDE. And I think it works just great. And I think the Kotlin part is even available without any license for IntelliJ. I think you can also find the examples, all of them, in the repository itself. So like also the one which we were just discussing, where we have a traffic light, where we use more typed constructs to model traffic light state, where we have the controller, and so on, and where we have thrown way more individual processes, as we were just doing the example. So there's tons of examples in the repository. You can also find them online, organized by difficulty. Let me show you. So if you want to follow up on this, just go to kalasim examples. I think there's plenty of examples to get started with, also with some indicator how complex they are, and they're all focusing on different aspects of the library. So I think this is definitely a good start if you want to dig deeper here. All right, so we have 20 minutes to go. So let me talk for 10 more minutes, and then maybe we could have some more open discussion about how you feel about simulation, what you think is important when doing process modeling. But before we get there, let me sum up what we do once we have such a model. So let's briefly talk about the use of simulation for process optimization. And I think the most important advantage is that it allows for risk-free process change assessment. So whenever you want to change a process, you want to be very sure that you don't make it worse, because in many industries, I mean, diminishing your process efficiency costs you a lot of money. So you want to carefully prepare process changes. And by using a simulation model, you can do so. You can check what's happening if you revise a certain sub-process, if you hire more staff, if you fire staff, if you buy more equipment. So this is something that you can do easily, and it's totally free of risk. So I think it's an excellent tool to prepare process changes and to evaluate and assess them carefully before rolling them out into production. So let's talk about optimization in a bit more detail. So how can we use a simulation model to optimize a process? I think coming back to my manufacturing examples, I think, yeah, optimization always relates to planning, or very often relates to planning. And I think it's a very hard problem to be solved, because planning usually relates to, I mean, traversing a very complex search space, because you have many, many variables which you can adjust in a planning problem. And yeah, there's some kind of combinatorial explosion if you would consider all possible options to run or to configure a process. So it's a so-called NP-hard problem. Nevertheless, you always want to use better planning. You want to optimize your processes. And without diving into too much industrial engineering here, I think, yeah, there's many, many different objectives you may want to optimize. It could be efficiency, reduction of machine setups, cycle time reduction, and so on, personal load, shift planning, and there's quite a few more. And what you essentially always want to do when optimizing a process is you want to go for the low-hanging fruits first, because I think these days it's very tempting to always go for AI, but very often in complex processes, I think it's not the first thing to explore, but you rather want to do more classical type of process optimization, using rules, using classical optimization, which will often give you a performance boost already. But it's these classical techniques are sometimes a bit easier to control. So what optimization in process optimization is always about is about resource alignment. I think that's one of the key elements here, because we have different resources in any complex business process relating to man, material, methods, and for sure also the human factor. And what we need to do is we need to make sure that different resources are available in the same time frame, so that they can interact in order to achieve a certain goal. So for instance, a worker needs to go to a tool. The tool must be ready to execute a certain program, and then he can put a product to be produced on the tool to run the process. And just if all the four elements are available in the same time range, the operation can actually happen. So a lot of process optimization relates to aligning resources. So where's the simulation? I think there's this wonderful display which I got from pathmind.com, where they have worked out the idea of using simulation to prepare and to assess planning methods so nicely, because what it's about is we have simulation which we can steer into a direction to get a certain reward or a certain outcome. And clearly this is then a cyclic process. And then it's all about figuring out a scheme, a planning regime, to come up with the correct action, an action which will actually optimize the reward of our system. And deciding about what step to take, what action to take. For this, there are multiple options. So we could use classical rules, we could use optimizers, we could use reinforcement learning. And clearly very tempting is reinforcement learning, and we're also looking into this direction where we have the environment, which is now the simulation environment. And then we can use the simulation environment of our business process of interest, and we can throw it into the reinforcement machinery to prepare an action policy, which is also sometimes referred to as an agent. And then we can use this agent to steer, to plan our process or business process. And I think it's an exciting research direction, and there has been great progress over the last years. I'm not sure whether you follow the literature, but there was AlphaGo a couple of years, and it has been evolved into something called mu0 more recently. And there are two remarkable trends here. The first one is this planning AIs that become more general, so they cannot solve just one game, but they can solve a wide range of different games or applications. And what's also very remarkable is the amount of effort you need to build these AIs. So at the beginning, you still had to work out a lot of extra information to build these AIs. But these days, most of the reinforcement learning systems, they simply learn by playfully exploring a simulation environment. So what we have to do here to prepare an AI, like a planning AI, is we have to work out a simulation of our process of interest. then we can build a reinforcement learning agent to steer to govern this process. I mean, clearly it's still a long road ahead of us before we can, for instance, use reinforcement learning in a manufacturing setting. But technically and conceptually, we have most of the elements we need. We have a value function, we have a policy, there's different ways to define a reward function. So I think there's very exciting research initiatives going to this direction, and they all relate to having a simulation model of your environment. So that's why simulation is also in AI research an extremely important tool. What's still holding us back from bringing it into actual business processes to really use AI to govern and to steer business processes is the operationalization part, because I'm not sure who of you are dealing with ML ops, but it's really quite challenging. It's not just building the model, because you need a whole stack around the model to keep it running and keep it updated in production. And I think this is really the main challenge, which is holding many companies back from using reinforcement learning for planning in business management. Another very popular way which we use to optimize processes and which we can also assess in a simulation context is a mathematical optimization, where you basically try to formulate your problem or your planning process as a set of linear equations which you then try to optimize. And my favorite choice actually is constraint planning, because it's another type of optimization where you try to optimize goals with limited resources under certain constraints. And luckily, there's a wonderful library called OptaPlanner, which in my opinion is one of the most evolved AI constraint solvers. It's written in Java, but it interacts nicely with Kotlin. And as you can imagine, it's very easy to also embed and to connect this to a simulation model written with kalasim. And with OptaPlanner, we are doing pretty well when it comes to plan and to optimize business processes. It could be scheduling, it could be routing, could be packing, shift planning. I think there's it's a very open system which we can use for quite a few different use cases. It has very nice features, so it allows for over-constraint planning, continuous planning. You can pin planning entities, so it's also a very flexible tool, and it plays very nicely with kalasim simulations. So let's wrap up what we've learned today. So we've talked about simulation, and in particular, we talked about a library called kalasim, which is written in Kotlin and which allows to write simulation models. And these models can be consumed when working out optimization for processes. We can use it for integration testing, for game development, for capacity planning, for bottleneck research, and also for AI development. And we haven't touched quite a few features today. So for instance, what we can always do is we can control the execution speed of a simulation. So we can, for instance, make it run in real time. This is something which you may wonder, why is it needed? But you can use this very nicely when building a game or when really demoing a process to some user. Or even better, if you want to use a simulation to steer a system which is not part of the simulation. One of my favorite examples is system integration. I think, this is a winter school about software engineering. So I think you all have to think a lot about how to orchestrate components in larger architectures to play well together. And this is a problem for myself, my colleagues and myself as well. So when we prepare solutions for our manufacturing partners, we are also always struggling with testing these systems correctly. And by using a simulation, we can build wonderful test integrations, because process simulation allows to really work out a full integration of all the components which we later need in production. So what we do is we simply substitute the process of interest with a simulation model, and then we can run the entire process at an arbitrary clock speed, including all the components. So in this case, for instance, we could read out parameters to build some digital twin model of our process. We could then configure an OptaPlanner scheduler. We could put a scheduler UI on top of it. We could wire them all up via message-oriented middleware create some production dispatcher, create a tool interface, and for sure also consume the production plan back into the simulation model. And on top of all this, we can then define test assertions. So we also have a very structured mean to build a large-scale mock tests, which I think, yeah, it's an excellent tool, and we are using it successfully. And I think, yeah, everyone, at least in my place, really likes and embraces this approach to system tests. All right, we won't manage to do the second exercise today. So the idea was is to study processes at the gas station. So I worked out a process definition, and yeah, I would love to leave it to you to work through the exercise if you want to. For sure, you can always come back to me later on, also after the presentation, in case you have questions about how to solve this exercise. So what's next? So giving you a quick idea about the roadmap of kalasim itself. So we want to improve the process animation API a bit. We're currently working on environment snapshotting and branching using a library called Cryo. We're also digging into agent-based modeling. I think this is a very exciting topic. Clearly, the process mining toolbox needs some enhancements and improvements. And yeah, most of it, we simply want to use it more because I think it's just a great library and we can already do so many things with it. So what's next for you, maybe? So I think, yeah, there's the website. I already touched this briefly. So there's this example section. So if you're curious, feel always welcome to go through some of the examples which may relate to your use case. So to get started with modeling and simulation, let's skip this part. Yeah, I also included some references in the slides in case you want to listen to some more talks about where I have presented the library in different contexts. So here, for instance, we modeled different philosophers sitting around a table and trying to eat, which was a very fun exercise together with some colleagues from the Center for Advanced System Understanding here in Saxony. But yeah, so to really sum it up, I hope I could give you some overview, some insight about how at least we at SYSTEMA and how we try to approach process optimization. So it always starts with working out a process definition and doing process data analysis. Then it's about, taking these information, these insights, and modeling the process, which we then have to compare against the real process to make sure that it gives a good prediction accuracy. And once we have a solid simulation, then we can really start to explore a process optimization using constraint optimization, using classical mathematical optimization, or maybe using AI techniques such as reinforcement learning. So I think it became clear throughout the presentation that this is a very polyglot experience. So it's not just that we use one tool, like it's all Kotlin. I mean, it's definitely not that. So it's really that we use different tools to get there. So and clearly it's an opinionated view which I've presented, and I know other simulation experts and process specialists probably have their own experience. So I think in contrast to what the Mandalorian would say, there is no one way. I think there are many, many different ways to do process modeling and optimization. So what I presented today is a stack where we use mainly R for data analysis and process introspection, where we use simulation for kalasim. I basically give you a brief overview without digging into any details that Optaplanner is a good choice for optimization. And yeah, if you want to go even further into AI, I think RLab and Project Ray are very good libraries to also work out a reinforcement learning agent. Yeah, so to end with, I want to add a quick reference to SYSTEMA, the company where I'm working. So we, as I said in the beginning, work a lot on process optimization for various customers, from semiconductor to automotive to pharma. So I think it's, yeah, we really have a colorful portfolio of customers. And clearly, we do different things, starting from integration, automation, visualization, migration, optimization of manufacturing processes. So we need a lot of talent to do so. So that's why we are always hiring. So if you're interested in joining us for a job or for an internship or for CSIS project, Feel welcome to get in touch. Via the career@systema.com email. But for sure, you can also directly get in touch with myself. So I think we have many exciting projects going on. I mean, today we've just talked about process analysis and modeling, but for sure we do many other things as well. So we have lots of projects regarding scheduling AI. So we deal with factory physics, industrial engineering. Clearly, there's a lot of software development going on. We also use big data for quite a few customers. And what I really like most about it, it's not just academic, but we really try to solve real world problems in very complex, very exciting industries. All right, and I would like to close with the quote which we used to start with. So I hope it makes a bit more sense now. So yeah, we talked about complex business processes, which may seem like pretty messy and ugly in the first place, and there might seem that there's a lot of disarray. But actually, if you really dive deeper into these processes, there's usually a lot of beauty, a lot of order, and I think that's really the fascinating aspect when it comes to process modeling and process analysis. And that's why I also really love the subject. So it's really one of my favorites. So thank you all for joining. I think, yeah, you've been a great audience. Thanks for your questions. Thanks for being here today. And for sure, I also would love to thank the organizers for making this event possible. I hope to stay in touch with you. You can find my contact details here on the slide. And yeah, stay safe, stay healthy. And now I'm ready for your questions and comments. Thank you very much.